Good afternoon, everyone. So, welcome to my YouTube channel, Avatarm. I am Avatarm. Hope you all are good and you are doing well. So, today we are going to see another question on uniform convergence of function. So, let's start today's question. Let A and B belongs to R, B such that A is strictly less than B, and F and A close interval AB to R be a sequence of functions such that this sequence converges pointwise at some point x0 of AB interval, and derivative sequence is uniformly convergent to G on AB. Then option number 1 is Fn does not converge pointwise on AB. Second option is Fn does not converge uniformly on AB. Third option is Fn converges uniformly on AB, but derivative of F is not equal to G on AB. Fourth option is Fn converges uniformly to F on AB and F dash is not equal to G on AB. So here option number D is correct. It requires some proof. Actually, this is a statement of some theorem, and I have formed that theorem in terms of the objective question, MCQ. So today we are going to give its proof, okay? How it is uniformly convergent and derivative F is equal to G on AB. Option number D is correct actually. Okay, so let's start its proof. So Fn converges this sequence Fx0 converges. If it converges, what does it mean? It means F and x0 is Cauchy. Okay, this implies, so given epsilon greater than 0, there exists n1 belongs to n such that F n plus p x0 minus F n x0 is less than epsilon by 2 for all n greater than equal to capital N. Okay. Now, this sequence derivative function converges uniformly to G. Okay. So, there exists capital N2 belongs to N such that F n dash x minus n plus p. Okay. Because it is converges uniformly. It converges uniformly. So it is uniformly Cauchy. So I am writing in a full language. Okay. So Fn dash converges uniformly to G. This implies Fn dash is uniformly Cauchy. So they implies there exists capital N2 belongs to N such that F n plus p derivative x minus F n derivative x is less than epsilon upon 2b minus a. Okay, so this will work as epsilon for all n greater than equal to capital N2 and x belongs to closed interval AB. Okay. Now we can take maximum. Put n is equal to max of n1 and n2. Then both the inequalities will be true. Then what will we have? This This will be true for n greater than equal to n. We can replace n by n, and here we can replace n2 by n. Okay, then still it will be true. Then what we have? We have f n plus p x naught minus f n x naught less than epsilon by 2. Okay, for all n greater than equal to capital N, and derivative f n plus p x minus f n dash x less than epsilon upon 2b minus a for all n greater than equal to capital N, x belongs to a. Okay. So I am saying this combined equation 1. It means equation number means both the inequalities we have. Okay. Both the inequalities we have. Now, okay. Now, f n plus p minus fn is a differentiable function. Okay. Differentiable function for any x and y belongs to closed interval AB such that x is less than y. Apply mean value theorem. Okay. We are applying mean value theorem. Okay. So what does it mean? It means we will have f n plus p, okay, minus f n x, okay, minus f n plus p minus f n y is equal to x minus y, okay, f n plus p dash minus f n dash some j. Okay, this is mean value theorem. When we apply mean value theorem, then we for some j such that j is in between this. Okay, we can apply mean value theorem. You just apply mean value theorem and take the mode both the side, you will get this. Okay. Okay. Now what we have? You open this. This have f n plus p x minus f n plus p y. Okay. Sorry, let's solve it. Okay. What you will get? So what is this? Okay. So let's say it equation number 2. So we will solve it further. Okay. So what is this? What is this? F n plus p. Okay. X minus f n x. Okay, minus fn plus p y minus fn y. Okay, from equation number 2 we are using here equation number 1 we are using here. Use equation number 1. So it will be equal to using equation 1 we get what we get. This is equal to, we are solving equation number 2 and we are using equation number 1. So it will be x minus y. But from this is because xi is xy is in interval AB. So xi will be also in closed interval AB. But from equation number 1, what we have? This is less than equal to b minus a, epsilon upon to b minus a. Okay. So it will be less than equal to b minus a. Okay. So what is this? Because y is greater than x, so I can write this. Now you note that I have an interval a and b, and x and y are in between. So it means y minus x is less than, okay, b minus a, okay, and it is greater. So when we will divide it, it will be less than equal to 1. So this is this part, this and this combinedly is less than equal to 1. Okay, because from here we have to divide y minus x b minus a is less than equal to 1. So I have put this value here. So this implies fn plus p dash x minus fn dash x minus fn plus p dash y minus fn dash y less than epsilon by. Let's say it equation number 4. Oh, sorry, 3, equation number 3. Okay. Now fn plus p x. Sorry, I have made one mistake here. I am solving this equation. Sorry. I am solving this now. Here it's not derivative. I wrongly written derivative. Sorry. It is fn. It is fn na? Because we are working with fn and we apply mean value theorem. Because here is fn p fn. So why wrongly I have written fn dash here. So I have corrected here. So now fn minus fn x. Okay. What about this? I can add and subtract. Okay. Now I can apply here triangular inequality. Okay. Now I can use for this equation number 3. And what about this? Sorry, I can add y naught, fx y naught. Sorry, I should write x naught here. I am to use x naught here somehow. So x naught, I am adding x naught. Okay, x naught, x naught, x naught, x naught, x naught, x. Because equation number 3 is true for any xy, for any xy belongs to closed interval AB. This is true. So if I can take y naught in place of x naught, still it is true. It will be less than epsilon by 2. And from equation number 1, we have this is less than, this is also less than epsilon by 2. Okay. So both the terms are less than epsilon by 2. So we will write, here we write using 1 and 3. We get this is less than epsilon by 2. This is less than epsilon by 2. So that is epsilon. Okay. So what we got? We got fn plus px minus fnx less than epsilon for all n greater than equal to capital N, and x belongs to closed interval AB. Okay. So what does it mean? It means that it means that this is uniformly, Fn is uniformly Cauchy. This implies Fn is uniformly Cauchy on AB. If it is uniformly Cauchy, then what does it mean? It means it is uniformly convergent, because every uniformly Cauchy sequence is uniformly convergent. This implies Fn is uniformly convergent on AB. So let's say Fn converges to F uniformly on AB. It means its uniform limit is F. We are saying it's uniform because we have proved that it is uniformly convergent. Now we are saying that its uniform limit is F. Okay. Okay. Then define phi n t is equal to f n t minus fn x upon t minus x for t not equal to x. Okay. And phi t is equal to ft minus fx upon t minus x. Okay, where x belongs to closed interval AB. Okay. So here we should write fix x belongs to closed interval AB and define this. Okay. For one thing. for t belongs to AB and t is not equal to, for t belongs to AB and t is not equal to F. Okay. Now, okay. Now, limit t tends to x, phi and t. What is it? Limit t tends to x, fn t minus fn x upon t minus x. Okay. What is this? Because fn are differentiable functions. Okay. Differentiable functions. Fn's are differentiable functions. Okay. So, limit is fn dash x. Okay. For each n belongs to n. Okay. Okay. Now, next, phi n plus p x minus phi n x. What is this? What you will get? From here, what you will get? It will be, sorry, t. Here, right, t. So, t. What you will get? What is f and t value? F n plus p t minus f n plus p x t minus x. This is the value of phi n plus p. And this is f n t minus f x upon t minus x. Okay, absolute value. Okay, when we solve it, so this will come out 1 upon t minus x, and it will be f n plus p t minus f n t minus f n plus p x minus f n x. Okay. Now if we apply here equation number 3, so this is 1 upon t minus x absolute value. This is, what is this? By equation number 2. What we will have? Equation number 2. By equation number 2. By equation number 2, we have t minus x. Okay. F n plus p dash xi minus f n dash xi for some xi in between this. Okay. From 2, equation number 2. We have this one, but this and this will be cancelled out. Okay. Okay. And by equation number, now using equation 1, we have, if we use equation number 1, this is less than epsilon by 2. So this implies phi n plus p t minus phi n t, that is less than equal to f n plus p dash xi minus f n dash xi, but this is less than epsilon by 2 by equation number 1. So we have phi n plus p t minus phi n t less than epsilon by 2 for all n greater than equal to n, and t belongs to AB such that t does not belongs to X. So this implies phi n is uniformly Cauchy on AB, on X belongs to AB uniformly, and T belongs to on AB, it is uniformly Cauchy on AB except X. I'm deleting X from this interval. Okay. So except X, it is uniformly Cauchy. So if it is uniformly Cauchy, this implies phi n converges uniformly on closed interval AB deleted X. Okay. Okay. Now what were now limit n tending to infinity phi n t. What is its pointwise limit? Limit n tending to infinity phi phi, it is fn t minus fn x upon t minus x. But so what is this? But this means this is because fn converging to f uniformly. This is f t minus f x upon t minus x. Okay, which is phi t. Okay, phi t, which is phi t. Now I have done one result by. So I have done one result. So I am telling which lecture you have to see for that. Okay. So by lecture 10, by uniform convergence, okay, of functions, lecture 10, we have to see this lecture, because if you see phi n converging uniformly, and if you take any x phi n t for any fixed n, limit t tends to x phi n is nothing but fn t. Okay, it means pointwise convergence, so that sequence will be convergent, and phi n converges uniformly on AB. Then what we will have? We will have limit n tending to infinity, phi and t is equal to limit t tending to x phi t. Okay. So what is this? Okay. What is this? This is nothing but phi and t. What was phi and t? Phi and t. Sorry. 1 minute. 1 minute. Wait 1 minute. Phi and. So what is t tending to phi x? Okay. So by that result, lecture 10 number 10, we have here f and dash x x x here. Okay. So what is this? This is converging uniformly to gx. So point-wise it converts to gx. Okay. So what is this? What is this? It means this is t tending to x. F t minus f x upon t minus x. So what does it mean? It is f dash x. This implies f dash exists on AB and f dash is equal to G. Okay. Okay. So we have proved the result. We have shown that Fn converging uniformly. We have done it already. And derivative of f is nothing but G on AB. So we have done it. So what option is correct? So option number D is correct. Okay. So now we will see some example on it. Okay. Example. Now let Fn is equal to Fn x is equal to 1 plus x square upon factorial 2. On AB, sorry, 1 and 2. Okay. One minute. I should write here. X square upon factorial 2, x cube upon factorial 3, x 4 upon factorial 4, the x n plus 1 upon factorial n plus 1 on close interval 1 to 2. Okay. Okay. So we will see that what is the derivative? What is the derivative of this Fn x? is nothing but 1 plus x upon factorial 1 plus x square upon factorial 2 x cube upon factorial 3 but this sequence we have proved that in yesterday's lecture, okay, okay, that this sequence converges uniformly to e to the power x uniformly on closed interval 1 to infinity. So it will also convert to 1 to infinity, 1 to 2, because this is a smaller interval, okay, uniformly. So derivative function converges to some g, okay. Now if we can show that, what about fn1? What is fn1? fn1 is 1 plus 1 upon factorial 2, 1 upon factorial 3, 1 upon factorial 4, 1 upon. When n tending to infinity, it will go to 1 plus 1 upon factorial 2. Okay. I can write it 1 upon factorial 3 and so on. What is this? What is this value? This value is e to the power e minus 1. So fn1 converges. Okay. Now you can guess that, obviously. Now you see that. Now observe one thing. Now by theorem it should, by theorem, fn should converge uniformly, okay, to some f on 1 to 2. So what is that f? Can you guess? Yes, you can guess, because you have to select f such that its derivative equal to g. G is here e to the power x. Now if you first observe that, what is fn x? Fn x is x upon factorial 2. I can write it x cube upon factorial 3. Okay. X to the power n plus 1 factorial n plus 1. Okay. So I can add here 1 here and subtract 1. Okay. 1 is here. Now where this part will converge? This part will converge to e to the power x minus 1. So what is my f? F is e to the power x. Now you check what is the derivative. So fn converge uniformly to e to the power x minus 1. So now obviously, what is the derivative of this? E to the power x का derivative, e to the power minus e to the power x, and what is the derivative of 1? 0. That is my g. So it is verified. Okay. It means my theorem is correct. So thank you very much for today's lecture. This is important theorem. Sometimes it plays important role. So thank you very much for today's session. Like, share, comment on my YouTube channel, and also subscribe my YouTube channel. If you have any problem related to this topic or this lecture, you can comment me on my YouTube channel. Thank you very much for today's session. Thank you very much.